Hi class, welcome to our guided notes section now officially on Skill 1 from Unit 5. After completing our rather long introductory video, I believe we are now ready to go ahead and graph exponential functions with transformations. And just as a side note, this is also in your textbook, your Algebra 2 textbooks that we rarely use, but they're in section 7.2 of that book if you wanted to look there for more information. Now, in our intro to Skill 1 video, we looked at this model here, which is considered our parent function. And then for the parent function, though, a is 1. 1 times b to the x. And remember, the parent functions were different depending on what b was. If b was greater than 1, the parent functions sort of had exponential growth like this. And if b was between 0 and 1, because our bases are always positive, but if they're between 0 and 1, meaning a fraction, then our parent function kind of looked like that. And the values of the parent function are going to vary depending on what your b value is. So that's what you have to remember about exponential functions, is when you identify the parent function, it will be different depending on what that b value is. So you'll have to generate a parent table of values for each of these. It's not going to be the same one used over and over again like our previous functions have been. Okay, so that's the parent model, y equals a times b to the x, where a is 1. Now the hk version is when up in the exponent spot, okay, so all of this x minus h is all what the base b is being raised to. This is all in the exponent. This h is going to create a horizontal shift. And then outside of the exponent and down back at base level, you're going to see this added k. So this is our a being multiplied to the base b, being raised to a quantity x minus h. And then after all of that is done, adding k at the end. This is our hk version. And it's going to follow the same rules of transformations that all of our other previous functions have. So really quick, let's review graphing with transformations. So first you identify the parent. Then we will make a table of values for the parent function. So remember, in this case, it's going to be a different table each time. Then you identify a, h, and k. So h is in the exponent with x. Okay, so that's how you can distinguish the two, whereas k is on base level. It's not in the exponent, it's on base level, and it comes after all of this multiplication has happened. Then we make a new table with our transformations, and as a review, we always add the h value to the x coordinate, right? In the equation, it's subtracting, but in the table, it's adding. So in the table, you always do the opposite of what's happening in the equation. We always multiply a to the y value and then add k to the y value. So this is the same rules as all of our other functions. And then as another review, you basically, the a value, right? The a value has the power to either vertically reflect or stretch or compress your exponential curve depending on what the value of a is. If a is negative, it has the power to vertically reflect the graph over the x-axis. If the absolute value of a is greater than 1, so like even if a was negative 2 or something, but if you absolute value that, it becomes positive 2, which is greater than 1. So you kind of disregard the sign of a, you look at the size of it. If it's greater than 1, it will stretch the graph. If it's less than 1, between 0 and 1, so some kind of fraction, it will compress the graph. And then the h value, the one up in the exponent, will shift your graph either right or left, and it's always opposite of what you think. So if it's adding, it actually goes left. If it's subtracting, it goes right. And then your k value is going to move your graph. It's a vertical shift up or down, and it's always straightforward. You know, whatever the sign is what what the graph will do. Another thing to keep in mind is that with these functions, we talked about it in our previous video, the introduction video. These exponential functions all have horizontal asymptotes. So the parent function kind of looks like this. The horizontal asymptote is along the x-axis, right? And then the function kind of looked like that. This is our parent. This is our a times b to the x. Now that we're shifting these graphs vertically, right, we're adding these k values. So now we're going to be doing a times b to the x minus h plus k. That plus k will cause this parent function to shift up or down. And when the graph shifts up or down, the asymptote, the horizontal asymptote, shifts up or down with it. So the k will determine where your final horizontal asymptote ends up. So we know that in general, the a value, when we're graphing with transformations, creates vertical reflections, stretches, or compresses. So it acts as that value that can flip the graph over, stretch, or compress the graph. But with exponential functions, remember back to our intro to Unit 5 video, the a value has another important significance. It represents sort of an initial quantity, right, or an initial amount of whatever it is that's growing exponentially or decaying exponentially. It represents sort of that starting point, that initial quantity or initial amount of whatever this function is measuring. So that kind of is another important thing the a value represents. So we always want to kind of keep that in mind. Okay, so let's go ahead and start graphing these. For number 1, I want to first begin by identifying a, h, and k, and actually the base as well. We want to identify the a, the base, the h, and the k. So the a is whatever is being multiplied to the base. And in this case, there was nothing being multiplied to the base. So we're going to understand the a value to be 1. So because a is 1, that means there's not going to be a stretch, no stretch, compression, or reflection. Because a is 1. And remember, a is 1 in the parent function too. So this graph will look just like the parent function, y equals 3 to the x, except it will have shifted to the left 3 and down 5. So that brings me to the b value. So the base for this exponential function is 3. This is the determining value, determines the values for the parent function. Okay? And then h and k, so the h value will be -3 because it's based on the number that's in the exponent with x, and it's always the opposite sign. So it's x plus 3 in the equation, which means h will be -3. And then the k value here will be -5. So this graph is going to move to the left 3 and down 5. Okay, now let me go ahead and create my table of values for the parent function. So we're always going to have to do that with this. We're going to start with a parent and then move toward the transformation. So maybe I'll leave space so that I can add the transformations into this same table. And I'm going to use 2 negatives, 0, and 2 positives each time with these parent functions. I'm going to take my base b and raise it to each of those powers. So this becomes 1 over 3 squared, which is 1 over 9. 3 to the -1 would be 1 over 3. 3 to the 0 is 1. 3 to the first power is 3. And 3 squared is 9. And I just want to remind you of this feature of exponential functions. If I start here at 1/9 and then move from 1/9 to 1/3, what happened was I multiplied 3. Right, to get from 1/9 to 1/3, and then to get from 1/3 to 1, you multiply by 3. To get from 1 to 3, you multiply by 3. To get from 3 to 9, you multiply by 3, etc. So that's what makes, that's the essence of an exponential function, is when your y values are going up by the same multiple every time, right? Which is why they grow so quickly once we start getting into these whole numbers. Okay, that was just a quick review of that. Now let's go ahead and get the transformations going here. So I'm going to now subtract 3 from each of the x's. That's based on the h value of -3, right? So this is the x plus h, but h was negative, right? So it's x minus 3. A was 1, so the y values all get multiplied by 1, and then k was -5, so this is the a y plus k, but k was negative, so we subtract. So it's going to be 1 times 1/9 minus 5, 1 times 1/3 minus 5, 1 times 1 minus 5, 1 times 3 minus 5, 1 times 9 minus 5. So 1/9 minus 5 would be 4 8/9, right? Just a little bit, sorry, -4. Just a little bit above -5. And then 1/3 minus 5 would be -4 2/3. 1 minus 5 is -4. 3 minus 5, -2. 9 minus 5, +4. So these are my final values, my final y values. And then for my x's, it's -5, -4, -3, -2, and -1. So let's go ahead and plot those points. First one is at -5, -4, 8/9. So like almost -5, but not quite. This next point is -4, -4 2/3. So not as close to -5 as the last one. This point is at -3, -4. This point is at -2, -2. And the last point is at -1, 4. So there is we can see our crescent moon shape forming. But you might be noticing when the points start getting close together, the number they're getting closer and closer to this time is -5, right? If you look here at -4 and then -4 2/3 and then -4 8/9, those numbers are getting closer and closer to -5 because that is where our horizontal asymptote will be for this function, because this function shifted to the left 3 and down 5. So we should dot that horizontal asymptote in there, and then we can sketch our graph from there. So our function is not ever going to cross that. It's going to get closer and closer to -5 without crossing it, and then from there it forms this exponential shape, right? That crescent moon shape. You can see it started growing really fast once I hit the middle point. Once I hit the middle point, -3, -4, is where the graph began to shoot up really quickly. So you will notice that, by the way, when you are graphing these with transformations. Once you get to that middle point where x originally was 0 is where the graph will start to, the y values will start to spread apart a lot. And then on the left of that middle point is where it starts to get closer and closer to whatever its asymptote is, its horizontal asymptote, which in this case was -5. So let's write down the transformations. I didn't leave a spot for it, but I feel like it's helpful for us to do that when we're thinking about these graphs. So what happened was this graph shifted to the left 3 and down 5 from the parent function, from the parent graph of y equals 3 to the x. So this is the same shape. The shape you see here is the same shape as the graph y equals 3 to the x, except that it's been shifted to the left 3 and down 5, which is why our horizontal asymptote is now at 5. And then our domain for this function is all real numbers, because the graph is going to go forever to the left and forever to the right. I can basically plug in any x and get back a y value. But the range is going to be staying strictly above -5. Because normally the range stays strictly above 0, but this graph has shifted down 5. So it'll be allowed to go down to all numbers greater than -5. Now for the x-intercept, we're not able to solve for that yet. We haven't learned how to solve equations with logarithms. We're getting there. So later on, we will learn how to find x-intercepts of these graphs, but right now we're not able to. For the y-intercept, you plug in 0 for x. So I'm going to do 3 raised to the power of 0 plus 3 minus 5. So 0 plus 3 is 3. So this is just 3 cubed minus 5, which is 27 minus 5, which is 22. So my y-intercept for this function is 0, 22, which if you look at the graph makes sense, because the graph is going to want to shoot up forever and eventually get to the y-axis at 22. This graph is representing growth, right? My base of 3 is greater than 1 and my exponent is positive. So the graph is growing. The horizontal asymptote is at the value of -5, y equals -5. And by the way, yes, these functions are one-to-one. Even though they start looking really horizontal right here, there really is a different x value, or I should say a different y value for each x and a different x value for each y in here, because the y values are constantly moving closer to -5. So they're all a little bit different than each other, and they're constantly heading toward -5. So this function is one-to-one. It's not so it's always going to have a different x for each different y and vice versa. And then one thing I didn't mention on here is the fact that the function is increasing. So we can add that on. This function is increasing all the way from -infinity to +infinity because it's a growth function. So it's increasing the entire time. So in example 2, I can see here my equation. 6 times 1/3 to the power of x minus 4, and then plus 2. So my base in this case is the 1/3. The thing being raised to the power, that's your base. So in this case, this is what's going to determine my parent function. So the starting values of your parent function are determined by whatever the base is. So we have to make a new parent function table for each base. Okay, but then apart from that, I can see that my a value is going to be 6. So this is going to have a vertical stretch, right? It also has an initial value of 6. My h value is going to be +4 because to determine h, you look at the exponent, but then you do the opposite sign. It was -4, so that's +4. And then my k value will be 2. So it's going to move to the right 4 and down 2. So that also means, or sorry, up 2, excuse me. So that means that we will have a horizontal asymptote at y equals 2, because the whole graph, including the asymptote, is going to shift up 2. But let's begin with the parent table. So I'll put x here, I'll leave some space, and then 1/3 to the x, and I'll leave space around that as well. And I will generate the starting parent function values. So I use the typical parent x's, -2 to 2. So I'll raise 1/3 to the -2 power, and that actually flips to become 3 squared, which is 9. So this is going to be a decay. This graph is going to show decay, because when x is negative is when the y values are really big, and then as x gets positive, the y values will get smaller. 1/3 to the -1 basically takes the reciprocal of 1/3, which is 3. 1/3 to the power of 0 is 1. Anything to the power of 0 is 1. 1/3 to the power of 1 is just itself. And then lastly, 1/3 squared would be 1 squared over 3 squared, or 1/9. So you can see it's getting smaller, right? And then if you notice, from term to term to term to term to term, it's dividing by 3, right? Because the base is 1/3. So it's just dividing by 3 over and over again. 9 divided by 3 is 3, divided by 3 is 1, divided by 3 is 1/3, divided by 3 is 1/9. You can see that constant multiple or constant divisor that's happening. Okay, so now what we're going to do, that's our parent function. So now to get the rest of the graph, I'm going to add h to x. So each of these x's will add 4, because that's what we do to get our values, right? We add h to x. And then I'm going to multiply each of the y values by 6. That was my a value. And then I'm going to add 2. So this is going to be 6. I'm going to do over here. Sorry. 6 times 9 plus 2. 6 times 3 plus 2. 6 times 1 plus 2. 6 times 1/3 plus 2. 6 times 1/9 plus 2. And this is because this is a times the y value, right? The y value was the result of raising the base to the power of x, plus k. K was 2. Okay, so then 6 times 9 gives us 56, plus 2 gives us 58. So probably not going to graph that point because it's quite large. 6 times 3, 18, plus 2, 20. 6 times 1 is 6, plus 2 is 8. 6 times 1/3 would be 6 divided by 3 plus 2. So that's 2 plus 2, which is 4. 6 times 1/9 would be 6 over 9 plus 2. And then 6 over 9, you can divide both of those by 3. So then you get 2/3 plus 2, which is just 2 2/3. So probably what I will have to do is maybe I'll have my y-axis go by 2's. Okay, so this will be 2, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And I can graph all of the points from here on. I just won't be able to graph that last one. Okay, so let's do it. Oh, and these x's, this would be 2, 3, 4, 5, and 6. So I'm going to graph the point 3, 20, which is right here. Maybe we'll make a comment. Y-axis is being graphed by 2's. And then I have a point at 3, 20. Oh, I did -3. It should be +3. Sorry, +3, 20, +4, 8, +5, 4, +6, 2 2/3. So like right there. And it looks like it's dropping down like that. And it's going to flatten out right at the horizontal asymptote of y equals 2. Right? This is based off of the k value. The k value determines the vertical shift. So normally the function flattens out along the x-axis, but that has been shifted up 2 units. So now it's going to flatten out right at the y value of 2. Okay? So I'm going to add that on here, transformations. It wasn't on the outline, but it's an important part of this process. So this graph has been vertically stretched by 6. Okay? It has moved to the right 3 and up, to the right 4, excuse me. Moved to the right 4 and up 2. Okay, so that is why my new horizontal asymptote is at y equals 2. So there's our graph, and then we can see the domain, of course, is all real numbers because the graph will go left and right forever. But the range is now staying strictly above the k value of 2. So since this is completely above the x-axis, there will not be an x-intercept. And to find the y-intercept, we plug in 0 for x. So we do 6 times 1/3 to the power of 0 minus 4 plus 2. And then that equals 6 times 3 to the power of 4, because when you raise 1/3 to the power of -4, it takes the reciprocal 3 and then raises it to the positive 4, and then I have to add 2. So then 3 to the 4th is 81, so this is 6 times 81 plus 2. This is a gigantic y-intercept. And so that equals 488. So my y-intercept here is 0, 488, because on the left-hand side of this graph, right, because this graph is on the right side of the y-axis, and on the left-hand side it is shooting up so fast that it's going to, by the time it gets over to the y-axis, it'll be all the way up at the value of 488. And yes, this function is 1-to-1, as all exponential functions are. So in example 3, I wanted to just give you one example of what happens when a is negative. Because as we know, when your a value is negative, that means that we're going to have a vertical reflection. So I'm just going to write that down here in our transformations right off the bat. And when you have a vertical reflection, that means it's going to reflect down over the x-axis, because it's a vertical reflection, so it bends over the x-axis. And it's going to change this from being a growth model to just being a decreasing function. So I put a little star here. This is neither growth nor decay, because when we say exponential decay, we mean something that's kind of going like this. But this function is not going to look like that because it's going to take a growth function, which normally looks like this, and flip it over the x-axis and make it kind of drop down like that. So it's a decreasing function, but it's not necessarily exponential decay. It's a growth model that's been flipped down. The reason I say it's a growth model is because the b value is greater than 1, so the parent function represents exponential growth, but this negative a value is just going to flip that over the x-axis, and we would just call it a decreasing function. Not necessarily exponential decay, but just a decreasing function. So maybe I'll write that here. This function is decreasing for sure on the entire interval from negative infinity to infinity. But I wouldn't necessarily call it decay. I would just call it a reflection of what once was a growth model because the b value is greater than 1. Okay, but let's start with that. So my base is 1.5. So base equals 1.5, and so that will determine the parent function. Okay. Then after that, we notice that the a value is negative, right? It's also a value larger than 1, so there's also going to be a vertical stretch as well. I notice my h value is positive 2 based off the exponent, but then changing the sign. And the k value is 1, so I know that my horizontal asymptote will be at y equals 1 because of the k value. So let's start with our parent table of values. I'll run through my same x's as usual, and I'll just raise 1.5 to all of these powers. So this is 0.4 repeating, 1.5 to the negative 1, 0.6 repeating, 1.5 to the 0 is 1. Anything to the 0 power is 1. 1.5 to the first power is just itself. And then 1.5 squared is 2.25. So you can see it is growth, right? 0.6 is bigger than 0.4. 1 is bigger than 0.6. 1.5 is bigger than 1, etc. It started off as a growth model. But once I multiply all those by negative 2, right? And then they're all going to become negative. So then it will actually be decreasing, not growing once I do that. That's the a value because you're supposed to do a, y plus k. So I also need to add 1 to all of these y values based on our transformation rules. And then I have to add 2 to all the x's because you're supposed to add h to x. So this would be 0, 1, 2, 3, 4. And then this is 0.1 repeating. This becomes negative 0.3 repeating. Negative 2 times 1 plus 1 is negative 1. Negative 2 times 1.5 plus 1, that's negative 3 plus 1 is negative 2. Negative 2 times 2.25 is negative 4.5 plus 1 is negative 3.5. So now you can see it started positive, went into the negatives, more negative, more negative, more negative. It's just decreasing function now that we did all the transformations. So let's plot these points. So at 0, I have a point that's just a little bit higher than 0. So it's like right here, just a little bit above the x-axis. At x equals 1, it's now below the x-axis a little bit, negative 1/3. At x equals 2, it's at negative 1. At x equals 3, it's at negative 2. At x equals 4, it's at negative 3.5. So it's kind of going like this. It's a crescent moon, sort of, that has been reflected over this line y equals 1. So typically, it would have been up here had the a value been positive, but because the a value is negative, it vertically reflected that over this horizontal line, y equals 1. And so now it's just sort of this rapidly decreasing function, a reflection of a crescent moon over a horizontal line. So there's the graph. This is what it looks like when a is negative. So a being negative kind of, messes with our typical rules, I guess you could say. because it creates that reflection. The domain, though, is still all real numbers, right? X values are still all included, every single one of them, negatives and positives and 0. The range now, though, is less than the horizontal asymptote. Now all the Y values are below. Rather than above, they're below the horizontal asymptote. And then, again, we are not able to find the x-intercept at this point because we haven't learned how to solve exponential equations using logs yet, but we will. So stay tuned for that. The y-intercept we can find, actually I can see it's right here because it was part of our table. When x was 0, y was 0.1 repeating. So that'll be our y-intercept. And then, yes, this function is 1 to 1. And then let me finish the transformation. So there was a vertical reflection. That was because a was negative. But there was also a vertical stretch by 2 because a was 2. And then there was also a horizontal shift to the right, 2, and then up 1. And this was the reason for our horizontal asymptote being at y equals 1, because of that shift up 1 unit from the parent graph. So the rest of this outline is just practice for you. I have 3 graphs that I want you to try. I'd like you to pause the video here, give them a try, see if you can answer these questions, and why don't you add transformations there as well to each of them, just to make sure you're understanding that. Come back and check your answers with the video. Welcome back. Let's take a look at number 4. So number 4 was going to be a decay graph, right, going down this way because the base of 1/2 is less than 1, between 0 and 1. So this one is decay. And then the a value was 5, h was -1, k was -6. So here was my parent table where I just took 1/2 and raised it to the powers of -2, -1, 0, 1, 2. And that got me 4, 2, 1, 1/2, 1/4. But then I needed to multiply all of those by 5 and then subtract 6. So when I did all that, I got 14, 4, -1, -3.5, -4.75. I also needed to subtract 1 from every x. So instead of going -2 to 2, it went -3 to 1. And when I plotted the points, this was the graph I got here. I think I just went ahead and left the y-axis by 1s, and I just kind of went off the grid a little bit to get to 14. So there's my graph there. It's going to approach and flatten out toward the horizontal asymptote of -6. So we find that based on the k value. So even though my lowest y value in my table was -4.75, I know that k is where the graph will flatten off. So I want you to extend your graph beyond that last point and kind of have it start to flatten out and level off at the value of -6. So that also determines our range right there as well. So the y values will stay above that asymptote of -6. Domain is all real numbers. We can't find the x-intercept yet. That doesn't mean it's not findable. That just means that we are not at a stage in this class yet. We don't have the tools other than using Desmos or something to find it, but we will. We will come back and revisit these x-intercepts. Okay, y-intercept I found by plugging in 0 for x right here. So 5 times 1/2. It was 2.5, and then -6 was -3.5. We already talked about decay and horizontal asymptote. Yes, it's 1 to 1. I decided to throw in here a decreasing interval because the graph, since it is decay, it's decreasing the entire time from -infinity to infinity. The transformations are that it vertically stretched by 5. That was because of the a value. It went to the left 1 because of the h value and down 6 because of k. For number 5, your graph should look something like this. Just a quick comment, I actually did not graph the last 2 points because I wanted us to get a nice sense of the growth of this function, and I felt like if I scaled my y-axis too much, it would not be as easy to see. So I decided to only graph these 3 points, -2, -1/2, -1, 2, 0, 7, and then just kind of extend it the way I knew it was going on both sides. But I still found that the remaining y values would be 17 and then 37. So it's going to be growing really, really fast once I pass this value of 0, 7. So I just kind of had my arrow shoot up really steeply on the right. And then I know that on the left, it's going to drop down and flatten and level off by my horizontal asymptote determined by my k value of -3. So you can see that's right here, horizontal asymptote. So I have the graph kind of reach out toward that and continue, and I draw my dotted line in there at y equals -3. My base was 2, so that's why it was a growth equation. And then my a value was 10. There was no h value because only x was in the exponent right here. There was nothing else with it. That means h is 0. K was -3. So I just took 2 and raised it to all these powers, -2, -1, 0, 1, 2. I got 1/4, 1/2, 1, 2, and 4. And then I took those numbers, multiplied them by 10, and subtracted 3. And that's how I got these, -1/2, 2, 7, 17, and 37. And then plotted those points here. My domain is all real numbers. My range is staying above the horizontal asymptote at -3. Can't find the x-intercept yet, although we can see it has one. We just can't solve for it exactly yet. Y-intercept is 7, because if you plug 0 in here, you get 2 to the 0 is 1. And then you just have 10. 10 times 1 minus 3 is 7. This graph is growing because the base is greater than 1 and the a value is positive, so it's not going to reflect down or anything. Horizontal asymptote's at -3. Yes, it's 1 to 1. Since it's a growth function, it's increasing the whole time from -infinity to infinity. So the transformations are, there was a vertical stretch by 10, and also the graph shifted down 3. Lastly, with number 6, we had a base that was just a little bit lower than 1, right? It's just slightly under 1, 0.8, which does make it a decay graph. But you can see it's not a very fast decay. It's kind of a slow decay, right? A flatter decay graph because the rate is, it's less than 1, but just a little bit less than 1. But it's still decay, right? It's still decay. So the parent function is when I just take 0.8 and raise it to the power of x, which is what I did here to begin. My a value is 2, my k value is -3, my h value, h value is -3, my k value is 5. So I started by taking 0.8 and raising it to -2, -1, 0, 1, 2. I got these decimals here, 1.565, 1.25, 1, 0.8, 0.64. Then I subtracted 3 from all the x's to get -5, -4, -3, -2, -1. I multiplied all these y values by 2, doubled them all, and then added 5. And so that's how I got 8.125, 7.57, 6.6, 6.28. So here's what it looks like when I plotted it out. And I know that the graph is going to be reaching toward and flattening out at 5 based on my k value. That's my horizontal asymptote. So I dotted in that line and had the graph extend beyond the points I found to head down toward and flatten out at 5. Since it's a decay graph, it is decreasing from -infinity to infinity. Oh, the y-intercept, sorry, skip that, is what you get when you plug in 0 for x. So that's 2 times 0.8 to the power of 3, right? 0.3 is 3, plus 5. And then 0.8 to the power of 3 was this decimal right here, 0.512. So when you multiply that by 2 and add 5, you get 6.024. So it's hitting the y-axis just slightly above the y value of 6. The transformations are that it had a vertical stretch by 2. It shifted to the left 3 and up 5 from where the parent graph would have been. And here is our general shape. So tomorrow is when I'm going to give you more of these to practice. And hopefully you'll be feeling really good with these graphs heading into next week. And again, as always, email, text with any questions. I will try to help clarify as much as I can. Thank you for your continued participation. Bye-bye.